I'd like to introduce Professor Satendra Sharma, who is Dean and Professor of Physics in the Faculty of Science, Yobe State University, Damaturu, Nigeria. And today he'll be speaking about nuclear structure and IBM. Over to you, Professor Satendra Sharma.
Thank you, Madam.
Most welcome.
Nuclear structure refers to arrangement and behavior of protons and neutrons within the nucleus. The study of nuclear structure is fundamental to understanding how atomic nuclei behave, their stability and interaction that govern nuclear reactions. The key factors influencing nuclear structure include the nuclear-nuclear interaction. The nucleons interact through the nuclear forces which bind them together. These interactions are complex, involving both short-range attractive forces and long-range repulsive forces. Next slide, please. Next slide, please. Next. Thank you. Now, the shell model. This is simple yet a powerful model for describing the structure of nucleus. It treats protons and neutrons as moving in discrete energy levels or shells, such as like the electrons in atomic shells. The shell model helps explain the stability of certain isotopes and various observables. Collective model. This model describes the nucleus as a system that can exhibit collective behavior like rotations, vibrations due to the collective motion of nucleons. It accounts for phenomena such as nuclear deformation, the shape, that is shape, and the nuclear excitations. Next is deformation and shape. Nuclei may not be spherical. They can be on prolate or oblate shapes. This deformation is particularly important for heavier nuclei that can have unique phenomena such as nuclear rotations. Next slide, please. The nuclear structure can be studied by shell model or interacting boson model or the geometrical models. Thank you. Next slide, please. Now, pairing and collective excitations. In certain nuclei, pair of nucleons interact in a correlated way, leading to collective excitations. These correlations are key features in nuclear structure and can result in behavior such as superfluidity and the formation of the collective vibration states. Next is interacting boson model. This model was it is used to describe the collective aspect of nuclear structure, particularly low energy excitations. It was developed by Arima and Yakello in 1970 and onward. The IBM has become an essential tool for understanding collective motions, including vibrations, rotations in even nuclei or even odd A nuclei. Next slide, please. The key concept of IBM is boson representation. IBM treats the nucleons as collective excitations that can be represented by bosons. A boson is a particle that obeys Bose-Einstein statistics, and in IBM, nucleons are approximated as boson pairs. There are two types, S bosons and D bosons. S for L orbital angular momentum L is equal to 0, while D for L is equal to 2. Next slide, please. Hamiltonian. Then the dynamics of IBM are described by an effective Hamiltonian that includes term representing the interactions between the bosons. It includes boson-boson interaction, single particle excitations. Then symmetry groups. IBM uses group theoretical methods to classify nuclear states. There are main symmetries, U6 symmetry. This is a fundamental group symmetry of IBM describing the full space of boson configuration. Second is SU3 symmetry. For certain nuclei, the IBM can reduce to SU3 symmetry, which describes the rotational behavior of the deformed nuclei. This symmetry is often associated with rotation, deformation, and different shape of the nucleus. Next slide, please. Next is phase of nuclear motions. IVM describes various phases of the nuclear collective motions, U5 limit, SU3 limit, and O6 limit. U5 correspond to spherical nuclei that represent a traditional model where the nucleus undergo collective vibrational excitations, while the SU3 limit, this corresponds to prolate or oblate deformation and deformed nuclei and represent a rotational mode where nucleus undergo collective rotational motion. The third one is O6 limit. This corresponds to the nuclei with soft shapes, where the transitions between vibrational and rotational mode is more flexible. Next slide, please. Interacting boson approximation. Dominant interaction between the nucleons has pairing character. Two nucleons form a pair with angular momentum J or L is equal to 0 called S pair and J equal to 2 D pairs. Next slide, please. Approximation is also there. Next, microscopy of the IBM. In boson mapping, fermions are represented as given below. And mapping of operators such as Hamiltonian should take account for Pauli's effects. Next slide, please. Interacting boson model. Describe the nucleus as a system of n interacting S and D bosons. And Hamiltonian is HIBM as written here. And it is justifying from the shell model as well as geometrical model. Next slide, please. U6 algebra and symmetry. There are 6 creation and 6 annihilation operators as shown here. And Hamiltonian and other operators can be written in terms of the generators of U6. And the harmonic Hamiltonian has U6 symmetry as shown here. And it is having additional term breaking U6 symmetry. Next slide, please. IVM Hamiltonian for rotational invariant Hamiltonian with up to n body interactions is shown here as HIBM. The single boson energy is epsilon and boson-boson interaction is mu in the IBM Hamiltonian are soluble. Next slide, please. These are the dynamic symmetries for different sub-algebras U5, SU3, O6, SO6, SO5. And their soluble limits are given below. Next slide, please. Dynamic symmetries of IBM. Here, the Hamiltonian H for IBM, general Hamiltonian is written here. And it is having different, sub groups also here in the second form. The coefficient n, eta, and k are certain combinations of the coefficients, the epsilon and the nu. Next slide, please. The soluble IBM Hamiltonian is shown here for the 3, SU5, SU3, and SO6 limits. Next slide, please. U5 vibrational limit. Here, for U5 especially, this is the Hamiltonian and eigenvalues are given in the form of E. Here, K1, K4, and K5, which are related to C0, C2, C4, can be obtained with the energy available, experimental energy of ground state to first excited state, first 4 plus state, and second 2 plus state. Next slide, please. These are the features of the SU5 limit. The triplet of 0, 2, 2, 2, 4, 4, 1 states is in neighborhood of twice of the energy of first excited state. Quadrupole moment of first excited state is 0, while the energy ratio R4, 2, which is the energy of E4 ground to 2 ground, is 0. Next is gamma band exhibit a staggering pattern in its energy levels with states like 2 gamma and 3 gamma and 4 gamma, they are close. Then 5 gamma, 6 gamma are close, and so on. In contrast with triaxial rotor with the symmetry parameter gamma naught display different staggering, which is 2 gamma, 3 gamma are close, 4 gamma, 5 gamma is close, and so on. 2 nuclei that serve excellent example of SU5 type are 64 Zn and 76 Se. Next slide, please. These are the typical U5 vibrational limit spectra, one shown for 110 CD on left hand side, and you have on the left hand side the experimental energy levels are there from experiment, while on the right hand side of the first figure it is U5 limit. Now here ND, nu or L pi, they are representing the property of every state. Like if it is 0 plus, then 0, 0, 0 plus, then 1, 1, 2 plus, and so on. And next slide, please. Now this is the SE3 rotational limit. The Hamiltonian is there and eigen values are there. Here K2 lambda square plus mu square plus 3 lambda plus 3 mu plus lambda mu. It is the Kashmir operator here of SE3 limit. Next slide, please. This is the typical spectra for this SU3 limit. The example is 156 GD. On the left hand side is experimental energy spectrum for the lower states up to 2 MeV, while on right hand side is from SU3 limit. Next slide, please. These are the features of SE3 limit. Here the again energy ratio is 3.33. Energy gap between the two neighboring levels of ground state rotational band and beta vibrational band remains constant. The energy levels of states with identical spins are equivalent for both gamma vibrational and beta vibrational bands. This means that the gamma and beta bands exhibit degeneracy for the same spin in two different bands, beta and gamma. There exist many bands with different properties, like ground state band k pi is equal to 0.1, beta vibrational band k pi is equal to 0.2, gamma vibrational band for k pi is equal to 1 plus, beta 2, gamma gamma, and so on bands are there. The band mixing parameter is 0 here between the gamma and ground band branching ratios. The B2 ratio from 0 beta to 2 ground to 2 gamma to 0 ground is 1/6, while B2 ratio for 2 gamma to 0 ground and 2 gamma to 0 ground is 0. These are the typical features of IC3 limit. Next slide, please. This is O6 SO6 gamma unstable limit Hamiltonian, and their eigenvalues are also there down, and ABC are the constants can be obtained from the energy levels which are available from the experiment. Next slide, please. This is the typical energy spectrum. You can see here it is for 196 PT. On left hand side is experimental and right side is O6. Next slide, please. Now these are the properties for O6 limit. Like ground band had a well-defined notation. Gamma band exhibit energy level pattern that show staggering. As I explained before, 2 gamma is 3 gamma, 4 gamma is close, 5 gamma, 6 gamma is close, while 2 gamma is little away. It is unlike the triaxial rotor, where 2 gamma, 3 gamma are close, 4 gamma, 5 gamma are close, and so on. Beta band, next is beta band follows the sequence of 0 plus 2 plus and 2 plus states with a significant energy gap. Then 0 beta state is positioned at the lower than the 3 gamma state, 3 gamma. Then E2 operator correspond represented by Q2 chi is 0, and selection rules well defined are there. The best example for this O6 are 134 barium and 196 PT. And here the energy ratio is R4 is R42 is 2.5. Next slide, please. This is the applications of IBM throughout the periodic table. And on y-axis is Z, on n-axis is N, and all the nuclei represented here. And you can see here the symmetry triangle representing the three dynamic symmetries and some, the nuclei lying on it, like from transition from U5 to SU3 is samarium ZD, while on U5 to O6 is RU, while on O6 to SU3 are rare earth nuclei, PT, osmium, krypton, etc. Next slide, please. Yes, this is, representing the different symmetries, SU3, SUX5, SO6, E5, and U5 in terms of the energy ratio R42. So, the various, the nuclei I identify by the different colors. You have the spectrum on the left-hand side, accordingly it is represented here for the nuclei across the periodic table. Next slide, please. This is, the Carsten triangle showing the symmetries, three dynamic symmetries, U5, SU3, and O6 on left-hand side. And still you have special symmetries, X5 and E5. X5 is on U5 to SU3 transition, while E5 is on U5 to O6. And here on the, on the right hand side, it is correlated with the Landau theory for rotational one. Like here U5 vibrator, you have rotational, and the rotational oblate and prolates are there. So this O6 is here, it is on the transition from SU3 rotor or prolate to the SU3 rotor oblate. Next slide, please. And T is representing here, T is representing triple point. Next slide, please. Now, this is the complete Hamiltonian of IBM and how we go about it, how to deal with it. The two-body interaction is shown here in the first equation, where E naught is core energy, epsilon S and epsilon D are the binding energy of S and D bosons. And there are the other Cl, Bl, and Ul are the boson-boson interaction parameters. So another form is shown here by equation 2, where the symbols have the different meaning here as shown down. So here what we have to do, a least square fitting technique is to be used to find out the optimized values of the four parameters. Or we take, if we are taking a nucleus which lies on SU5 to SU3 transition. So here A3, A4 are kept 0, while epsilon double dash A0, A1, A2 are to be taken into consideration, and we can use here the energy values up to, say, up to reliable spin assignment. So I have considered up to 10 plus, and we have to do the fitting, and we'll get the normalized parameters of this Hamiltonian. So it can produce the best lower and higher bands. And next slide, please. And these and so the first step is we use the FINT computer program to get the energy levels. Then we'll use FBM program to get the B2 values. Here we add two parameters, E2SD, which is alpha 2, and E2DD, which is √5 times of beta 2. E2 transitions are correlated in terms of alpha 2 and beta 2 as given below. Now here alpha 2 is called the boson effective charge, simply scaling factor affecting the B2 values, and beta 2 accounts for the nuclear shape transition. Here one interesting point is that this E2DD upon E2SD is 2.958 in SE3 limit, while it is reduced to 0 in O6 limit. So ABEM program gives the B2 values, means you can account for the E2, M1, and E0 transitions. The references are listed below. Next slide, please.
We have about 4-5 minutes left.
Thank you. These are the old references of Arima and Iakello. Next slide, please. Now, these are the latest references. Here, you can see the reference number at 6. We applied it for osmium nuclei. Next slide, please. Now here, partial energy level spectrum of N is equal to 96 to 108 of osmium is represented here. You can see the left side up, it is energy spectrum for experiment, while down is from IBM. Now here, if you see, if you'll go from 96 to 98, the energy 2 gamma, it is coming, there is crossing of 2 gamma and 2 beta. It is represented well here in the IBM, as well as the, variation of the energy with the N for different levels. On the right hand side up, it is representing the B2 values, 22 to 02 and 23 to 02, while down it is the B2 from 3 gamma to 2. So here we are taking 22 and 23. So here the hollow circle is the the experimental, while the cross is this IBM. Next slide, please. Now here again, it is, 4 B2 ratios are shown here on left-hand side, 3 gamma to 0/2. And cross is experiment and open circle is IBM here. And error var is shown here if the error is there. Down is 2 beta to 2 ground by 4 ground. And on right-hand side, 2 beta to 0 ground by 2 ground and 2 gamma to 0 ground by 2 ground. So 4 B2 ratios are represented well. Next slide, please. Next slide, please. Yes, this. So here, the parameters, optimized parameters are listed here for various, the nuclear, various, the N is equal to 96 to 108. And here 2 gamma to 2 ground by 4 ground is also shown here. And here, this the conclusion is that the IBM model is used to reproduce beta, gamma, and ground band. IBM parameters are used and are given, listed here. The interband B2 ratios of IBM are compared with the experiment, and presentation gives detailed description for these osmium nuclei. And high light their spectral features. These spectra are similar, those with W and hafnium nuclei, as they are also there in quadrant 2. The N is equal to 96 to 108 osmium isotope display rich structure of ground, beta, and gamma band. N is equal to 100. It is showing the X5 characteristics. So it is showing X5 features. And beyond which a saturation of deformation is also observed. Beta band is low and lie below the gamma band. It is represented here. Thank you so much. Thank you for listening me now.
Yeah, thank you, Professor Satendra Sharma. It's for a very beautiful talk on nuclear structure. We can have one question because of shortage of time. Any discussions or feedback?
Can I?
Yeah. Please go ahead.
Professor Satyen.
Yes, Prof.
Namaskar. Namaskar. Perhaps you would like to acknowledge Professor J.B. Gupta, because I saw his name, same
Yes.
J.B. Gupta, and he's of the same age group as Professor Mitra. I hope he's 93.
Yes.
So I hope you can speak few words for him.
Yes. Okay, yes. Thank you, sir, for guiding me. I joined my PhD in 1983 with Professor J.B. Gupta, and I completed in 1988, though the degree was awarded on 1st April 1989. He is a good human being. He is a very good researcher. He always gave me the proper guidance, and I have learned a lot under his supervision. Still, I am taking his advice. Always I am discussing with him. and I always pray for his good health. Still, he is very active in the research. Thank you.
He is around 93 or so. How old is he?
He is 90 plus.
Nine. Yeah,
Yes.
29 born. As
Yeah,
Professor Mitra,
29. So
I suppose,
around 90, sir.
it makes sense. Thank you. Sorry.
Thank you,
Thank
sir.
you very much.
Thank you, ma'am.
Yeah, thank you very much. And thanks both for the talks. And we should close the session now and go for a coffee break.